All right, now we're gonna do two half sections today. The first half section is going to be 6.4, which is separable differential equations, and the second half section is going to be 6.5, which is partial fraction decomposition. You did partial fraction decomposition last year if you took trig pre-calc at this school. It's possible you did it in your other pre-calc classes, other places, but I will remind you how to do it. So here would be your do now if this was in-person learning. So maybe pause, get this as a warm-up, and then unpause and come back here. Be aware that when you are adding rational expressions, you have to get common denominators. So like on number 1, you would multiply by x minus 3 over x minus 3. And on the second fraction, we multiply by x minus 2 over x minus 2. Just looking for how this comes together. Let me see here. There we go. There's your answers. Verify them. Whatever. So looking forward, no. Would have been a homework quiz if we were in class, but looking here, what on earth is a separable differential equation? Well, if you've been paying attention this entire chapter, I've actually been trying to teach every single problem as a separable differential equation. It's a differential equation that can be expressed as the product of a function of x and a function of y. It's called separable because you can break the variables apart like we have been doing this entire chapter. Like, in this case, we could multiply by dx on both sides, divide by f of y. We end up with dy over f of y is equal to g of x dx. When we talk about separable, we mean we can get the variables separated. We are able to separate it. And then we can antidifferentiate like we've been doing all chapter. Now again, I've been trying to emphasize that everything we've been doing is a separable differential equation. Here we go. Let's take this for a spin. Now it is important to do these in the correct order. The correct order that you want to do, you want to separate the variables, integrate, solve for c, and then solve for y. All right? So looking up here, we've got dy dx is equal to xy squared. So we start with dy dx is equal to xy squared. dy dx is equal to xy squared. And now we want to separate the variables. Again, this is your first step. Get x to the left, get y to the left, get x to the right. So looking here, we can multiply both sides by dx and divide both sides by y squared, so that we end up with dy over y squared is equal to x dx. All right, now we want to integrate both sides. Now in order to integrate both sides, we see this y in the denominator. We know from the rest of this chapter that it's going to be easier if we write this as y to the negative second. Dy is equal to x dx. Again, we want to get all the variables up to the numerator, rewriting with negative exponents, all that stuff. So that now we can integrate. So again, first step, separate the variables. Second step, integrate both sides. Now when we integrate both sides, we want to follow the rules. It looks like here we just have power rule. When we do the integration on this step, we want to put a plus c, but we only want to put it on one side. In general, we put the plus c with the x because we're solving this for y. All right, so looking here, we will have y to the negative second plus 1 divided by negative 2 plus 1 is equal to x to the 1 plus 1 over 1 plus 1. And again, just like I've been saying for the rest of this chapter, I would probably skip over the step where I actually write down the plus 1s, but since I'm trying to explain to you how to do this, I'm putting all of my steps down. So looking here, I happen to know that negative 2 plus 1 is negative 1, so this ends up being negative y to the negative first, dividing by negative 1 down here, just puts the negative out front, is equal to x squared over 2 plus c. And again, I probably would have skipped over this step right to negative y to the negative first is equal to x squared over 2 plus c. Once you get this, Notice that the directions do say to solve for y. I would not recommend solving for y yet. I would recommend solving for c. Why do I recommend that? It's a lot, just frankly, it's easier to solve for c in this step. So looking here, we have negative y is 1 to the negative first is equal to x squared over 2 plus c. We're just going to solve this for c. I think this ends up being negative 1 is equal to 16 divided by 2 gives me 8 plus c. Subtract 8. We get negative 9 is equal to c. All right, so now we have c. Just like we've done for the rest of the chapter, we're going to take that c and plug it in over here. We've now got negative y to the negative first is equal to x squared over 2 minus 9. And now we need to use any strategy we have available to us in order to get the y solved for. So there's a variety of different steps. You could do this in multiple ways. What I like to do first is get rid of that negativity. So I'm going to multiply both sides by negative 1, multiply by negative 1, multiply by negative 1. We now have y to the negative first is equal to 9 minus x squared over 2. Just flipping the order there. Now I need to take both of these sides and raise them to the negative first power. Raising to the negative first power is going to mean just take the reciprocal on both sides. So personally, I would like to rewrite this as y to the negative first is equal to 18 halves minus x squared over 2. Why do I do that? Well, 1, because it's true, and 2, because it allows me to put this as y to the negative first is equal to 18 minus x squared over 2. Write it as one fraction. So in the next step, where I invert both sides by taking the power of negative 1, remember negative first power just means reciprocate here. This is going to be y is equal to 2 over 18 minus x squared. And there I'm done. So again, we want to be very careful about this as far as the steps that you take. First step, separate the variables. Second step, integrate. Third step, solve for c. Fourth step, solve for y. Please make sure you do them in the order that I listed them there. Whew, look at this one. This one's hard. We got dy dt is equal to t e to the y equals 3, when t equals 6. Once again, we are ultimately going to want to get this so that we have y solved for. So we are going to want to get there. But before we get there, we want to separate our variables. So we've got dy dt is equal to t e to the y. Now we see that we don't have an x, so we can't follow that steadfast rule of x to the right, y to the left. Really what we want to look at here is what variable is in the numerator of the Leibniz notation. Numerator of the Leibniz notation is the y, so that's where y is going to stay. Y is going to stay on the left-hand side. So we're going to multiply both sides by dt and divide by e to the y so that we can get that e to the y with its differential there. So now we've got dy over e to the y is equal to t dt. Now some tricky things that I see here that divide by e to the y, that's scaring me. I'm just going to rewrite it as e to the negative y. dy is equal to t dt. Why do I do that? Now it's easy to drop this in. Integral, integral. We now can see on the left-hand side, I know we've done these types of problems before where we take the antiderivative of e to the negative y power. Technically a u substitution problem, but it's one of those quick ones where we can see if I was to differentiate it, I would have that factor of negative 1. So I would call this negative e to the negative y. And again, if I want to double check that, I just take the derivative of negative e to the negative y, and I have that chain of negative 1 that's going to cancel it out, is equal to t squared over 2 plus c. All right, so I've done my first two steps. I've separated my variables and I've integrated. Now I want to solve for C. Solving for C should not scare you. I mean, we've done all of the calculus that's required. Everything else is going to be pre-calculus and before. So looking here, I see y is equal to 3, so I've got negative e to the negative 3 is equal to, what's t? T is 6. So I'm going to have 6 squared over 2 plus c. So I'm in the step where I'm solving for c. Now let's just make this a little bit easier to deal with. Negative e to the negative third equals 36 divided by 2. I believe that's 18 plus c. Subtract 18. Now we've got negative e to the negative 3 minus 18 is equal to c. I now have my c. Could I put that as a decimal value? Sure, but why would I? Why on earth would I? Now I'm going to just put this into my general solution where I've got negative e to the negative y is equal to t squared over 2 plus c. So minus e to the negative third minus 18. So it looks like I've found my c, I've plugged it back in. Now all that's left for me to do is to solve for y. Now to solve for y, I know that I want to get e by itself so that I can ln to get rid of the e. To get rid of the negative, I'm just going to negate everything. So this is going to be e to the negative y is equal to negative t squared over 2 plus e to the negative third plus 18. Again, I know to unexponentiate here. To unexponentiate, I apply an ln. So I'm going to have negative y is equal to ln of negative t squared over 2 plus e to the negative third plus 18. One of the pitfalls that I see people doing here, they try to do something with that ln. You cannot do anything with that ln. It has to remain as that quantity because when we have a sum inside of a log, we cannot simplify that at all. We cannot expand it. We can't distribute the ln. That's just not a thing. Now all we have to do is get rid of that negative, so it's going to be y is equal to negative ln of negative t squared over 2 plus e to the negative third plus 18. And that's it. So again, steps you want to follow: separate the variables first, integrate, solve for c, and then solve for y. Do them in that order, and you won't cause yourself any sort of distress on these problems. Next one we see here. Oh wait, that was me doing the problem over again. You can see I just changed the order down here to make it a little bit easier to write. Ew, boy. I believe this is our last separable differential equation. By the way, we know these are separable differential equations. I haven't iterated it exactly, but when you see both the dependent and the independent variable in the problem, that's how you're going to get the key that you're using separable differential equations. I'll try to be very explicit on the test as far as that's concerned. Now here again, we have dy dx is equal to 2 minus y. I put this one up here for the simple fact that a lot of people, when they try to do this, they try to add y to both sides. I want to really be clear here. You should not be using addition or subtraction for separating your variables. You should only be using multiplication and division to get them variables separated. So looking here, again, I'm multiplying by dx. And in this particular case, I want to divide by 2 minus y. Now when I look at that, everything from the right-hand side is gone, except for dx. That's going to make the right-hand side a lot easier to integrate, right? Over here, we're going to have dy over 2 minus y. And actually what's nice about this particular problem, this allows us to get a strategy for the next technique that we're going to use, the partial fraction decomp. Whenever you see a variable in the denominator, if that power is a 1, you're going to be using the ln here. Technically, this would be a u substitution problem, but it's one of those simple u substitution where we can see the chain is -1. So this, when I integrate both sides, on the left-hand side, I'm going to have the ln of 2 minus y, but I need to counteract that chain and have that negative, is equal to the integral of 1 dx is just x plus c. Now, we know that we're talking about where y is equal to 0. Since we're talking about where y is equal to 0, this quantity right here is always going to be positive, so we technically don't need those absolute value brackets. So I'm just going to remove those when I'm solving for 0, 0. So I have my x value is 0, that's my x value, and that's my y value. So I'm going to have negative ln of 2 minus 0 is equal to 0 plus c. Well, the right-hand side is actually pretty easy to solve, isn't it? 0 plus c, that's just c. I think the left-hand side is easy to solve as well. 2 minus 0 is 2, and the ln of 2 is just ln of 2. So that means that c is equal to negative ln of 2. I go back and I plug that in, and I think I'm going to have enough space to put that up here. So we have negative ln. Again, since we're talking about 0, 0, this is not going to be, the absolute value is not going to be necessary. So 2 minus y is equal to x plus c. But our c is negative ln of 2. All right. Now, only thing left for me to do is to solve this for y. So now to solve this for y, I know that I'm going to have, let's see, divide by negative, so it's going to be ln of 2 minus y is equal to negative x plus ln of 2, right? Okay, so there's a couple of ways that I can tackle this next part. One way that I could do, no, there's not a couple of ways. Never mind, my bad. Okay, so the next thing that I want to do here is I want to exponentiate both sides. So this is going to be 2 minus y, and I'm using a base of e, so on the right-hand side, I'm going to have e to the negative x plus ln of 2, remembering from trig pre-calc that e on ln's. So now I've got 2 minus y is equal to e to the negative x plus ln of 2. Well, over on the right-hand side, just a couple of tricks that I have here. E to the negative x plus ln of 2 is the same thing as e to the negative x times e to the ln of 2. Just using my rules from, what was it, Algebra 1, Algebra 2, a sum in the exponent is the same thing as a product of the powers. And now I see e to the ln of 2. E to the ln of 2 is just 2. So this becomes 2 e to the negative x, using some of those tricks. Again, this is not a calc part of the problem, but it is still something that you should know how to do. Now I've got 2 minus y over here. Again, I want to subtract 2 from both sides. So I'm going to have, let's see, negative y is equal to 2e to the negative x minus 2. Divide by negative 1. I'm going to get y is equal to negative 2e to the negative x plus 2. I would probably, just because I like to write these in the prettiest way possible, 2 minus 2e to the negative x is how I would put it. But either way, as long as you have y solved for, you're good. Whew. Yeah, there we go. Now we have partial fraction decomposition. Again, if you took trig pre-calc at collegiate last year, you know this process. This process is the reverse of that warm-up that I had up there. So if f of x is equal to p of x over q of x, where p and q are polynomials with the degree of p less than the degree of q, and if q of x can be written as a product of distinct linear factors, then f of x can be written as a sum of rational functions with distinct linear denominators. Okay, that's a lot of things. Put this as a real quick checklist. F of x is a rational function. So rational function just means polynomial up top, polynomial down below. Check, we move on to the next step. Next step is the bigger degree in the denominator. If that's a check, we go on to the last check. Last check is denominator is factorable. Now I will tell you that there are different strategies if we have repeated factors or if we have nonlinear factors in the denominator. AP tells us that as far as partial fraction decomp is concerned, we will be limited to two distinct linear factors in the denominator. So that's what we're going to work with in this class, as long as the denominator is two distinct linear factors. Now I know all of that looks confusing. Trust me, it's not that bad. There's a lot of work to it though, whatever. All right, so right here we have this rational expression. Now, I will tell you that this is ultimately a strategy for finding an integral. So let's just pretend, just for the sake of argument, I'm taking this problem, and instead of trying to do the partial fraction decomposition, I know that ultimately what I want to do with this problem is not just decompose it. Again, I'm talking about this course, so I know that eventually I'm going to want to do the integral of this fraction. The first step is going to be the partial fraction decomposition. Everything beyond that is going to be very formulaic. All right, so we're going to run through that three-step checklist. Number one, is this a rational expression? The answer is yes. To see how it's a rational expression, look at the numerator. It's a polynomial. It's a linear function. Okay. Denominator. It's a quadrilateral. Quadrilateral, which would be a polynomial, right? Okay. Cool. So we have not a quadrilateral. Oh my gosh, a quadratic function. My gosh, I had a blank on vocab there for a second. Ever have that where you just can't remember what a word is? I just had a heart attack forgetting what quadratic function was. Whew, sorry about that, kids. So we have a rational function here because we have a polynomial over polynomial. Second, the degree in the denominator should be bigger than the degree in the numerator. Again, we have a quadratic in the denominator, which is a degree of 2, the degree of 1 in the numerator. That's perfect. The last check that we have to do is the denominator factorable? Well, the denominator is factorable, so the first step that I'm going to do is I am going to factor it. When I factor it, I'm just going to put it in the denominator here. So numerator is not changing. X plus 5 over, I want to factor x squared plus x minus 2. Factoring x squared plus x minus 2, I want two numbers that sum to be 1 and have a product of negative 2. Okay, I got it. X plus 2 times x minus 1. I believe that works, and the differential should stay out here as well, right? So now we know that all three of those items in the checklist are met. That means that this fraction can be rewritten as a sum of two rational expressions. And those two rational expressions is going to be equal to the integral of some number over one of the factors plus another number over the other factor. So when we're doing this, again, you will have two distinct linear factors. You're always going to write it out as a over whichever factor plus b over whichever factor. It doesn't matter which factor you put under which one because you are choosing a and b. Now the next part of this is going to be entirely scratch work. I'm going to do this in red to demonstrate that this is not actually part of the problem. Now remember, I know that this expression has to equal this expression. That would mean if I did a times, not a times, but if I did a over x plus 2 times x minus 1 over x minus 1, like I should have been doing in the do now, plus b over x minus 1 times x plus 2 over x plus 2, that's going to be the same thing as x plus 5 over x squared plus x minus 2. I'll be honest, I don't actually put this on my paper every single time because now I can see that I have a times the quantity of x minus 1 over, let's see, both of these are going to have the same denominator, so I can see that both of them are going to be over x squared plus 2x minus x, so plus x minus 2 plus b times the quantity of x plus 2 equal to x plus 5 over x squared plus x minus 2. So what I can see now is the denominator is the same, which means the numerator must be the same. When I do these problems, as soon as I have a over x plus 2 plus b over x minus 1, I set up this equation where I have a times x minus 1 plus b times x plus 2 is equal to x plus 5. Just to run you through how I do that from this work up here, I do a times the other one plus b times the other one is equal to the original numerator. All right? Now my step is, how do I figure out what a and b are? To figure out what a and b are, I use something called the Heavicide cover-up method. You could really you could do this a number of different ways, but this is the easiest method that I've found. Basically what we're doing here is we're going in and we're making up an x value. The key here is whatever I make up my x value to be, it has to be the same here, here, and here. As long as that's true, I maintain my equality. There's two good values to use and infinite okay values to use. The two good values to use are x equals 1 and x equals negative 2. If you're wondering how I get those are the values that make this equal to 0 and this equal to 0. Because when I plug x equals 1 up here, I have a times the quantity of 1 minus 1 plus b times the quantity of 1 plus 2 is equal to 1 plus 5. Basically, what I had there is, since I'm using my value of 1 that makes this equal to 0, I can, that's why it's called the Heavicide cover-up method, I can cover up that term. Basically, I've just got b times 1 plus 2 is equal to 1 plus 5. I had to turn on my webcam so you could see what I was covering up, because I used my hand for that one. This becomes 3b is equal to 6, which means b equals 2. So I can find out my b really easily. Finding out my negative 2, technically what I have to write down is a times negative 2 minus 1 plus b times negative 2 plus 2 is equal to negative 2 plus 5. Honestly, I don't write that out every single time. What I do is I take my hand and I cover up the one that I'm trying to say is a non-issue. I made x equal to negative 2. That's making this not there. I just cover it up. I have negative 3a is equal to 3. So again, that's negative 3a is equal to 3. Which means, divide by negative 3, a is equal to negative 1. So again, all of this is scratch work. Really what I'm dealing with is the integral of a, what did I say a was? A was negative 1 over x plus 2 plus b was 2, right here, over x minus 1 dx. And here's where it gets extremely formulaic. So I have a linear factor in my denominator. The antiderivative of a linear factor is going to be ln. And when I look at my ln, there's actually no chain because I just have a coefficient of 1 out here. This is going to be that negative 1 ln of the absolute value of x plus 2 plus 2 ln of the absolute value of x minus 1 plus c. Now, if you're taking the AP test, this will usually come up on a multiple choice question, and it's kind of a toss-up whether they have the expanded form or the condensed form, so you just kind of have to get into the habit of doing the condensing. I will inform you that on my test, I don't care whether you leave it expanded or condensed, but if I was to condense this, I can see this negative 1 can go up here as a power of negative 1. So this x minus 2 is going to go in the denominator. This would be ln, putting x plus 2 in the denominator. And this 2 can come up here as an exponent, which makes this absolute value bracket unnecessary. So x, whoopsies, not plus 2. X minus 1 squared plus c. So again, that step right there is just condensing from our trig pre-calc course. If you need practice on condensing and expanding, office hours is the best way to do it. But again, what I'm looking for is this one right here. Or you can condense it if you want to practice. And I believe we got it right. And again, I will remind you guys that the final answer, it doesn't matter which one you chose as A and B, because it will still, you chose where they are. So it's going to, you choose the order there is what I'm trying to say here. So we got 2x plus 16 over x squared plus x minus 6. So yes, it is a rational expression. Yes, the degree is bigger on the denominator. And yes, it is factorable. So here I would jump right to A over plus B over, and you can see exactly how I would run through this problem. Multiplies to be negative 6, adds to be 1. X plus 3, x minus 2. And again, it doesn't matter if you put x minus 2 in first and x plus 3 second. You chose where they go, so ultimately it don't matter. All right. Now, what does matter is once you declare what A and B are, that you set up your equation correctly. So again, when I set up my equation, I don't actually do the adding the two rational expressions together. I say A times the other one, A times x minus 2, x minus 2 plus B times the other one, x plus 3, is equal to the original numerator. And now I just do the cover up. The cover up, I'm going to have x is equal to 2 is going to make this equal to 0. And x is equal to negative 3. I don't know if it helps to see where my hand's going here. But for the first one, x equals 2 allows me to cover up that first one. We're going to have b times 2 plus 3, so 5b is equal to 2 times 2 plus 16. So again, looking at that, I've got b times 2 plus 3 is equal to 2 times 2 plus 16. I mean, you might not even need to put that down. I could see in my head that this is 5b is equal to 20, or b equals 4. All right, cool. So I found b. Now I just need to find a. To find a, do the reverse. You can't see it, but I'm covering up my b times quantity of x plus 3. Because really, this is just going to be a times negative 3 minus 2 is equal to 2 times negative 3 plus 16. Again, I probably wouldn't put that step down because I can just see this is negative 5a is equal to 10. So a equals negative 2. I've now got my a and my b. I go up here, and I've got integral of a over x plus 3, so a is negative 2 over x plus 3 plus b 4 over x minus 2 dx. And now it's extremely formulaic. Again, since we see a linear factor in the denominator, it's going to be numerator ln of the absolute value of the denominator plus numerator ln of the absolute value of the denominator plus c. And if we want to practice at the condensing here, I think since all of these exponents end up being even, doesn't matter about the absolute value, we just have x minus 2 to the 4th over x plus 3 to the squared plus c. So again, either of these two answers is acceptable. Yeah. Ways that I can make this harder, I can make the factoring more difficult. So looking here, we have x minus 13 over 2x squared minus 7x plus 3. Again, probably the hard part on this one is getting what the factored form is in the denominator. And just so you know, I did pause the video right there to get what the two factors were. So again, that took me a little bit of time just because I'm a practiced at all my algebra 2. I happen to know that one of the factors was x minus 3. The other factor was 2x minus 1 dx. Again, I know my my equation that I want to use for the Heavicide cover-up method is going to be a times the other one plus b times the other one is equal to the original numerator. Now this makes it a little bit more difficult to figure out what you plug in for a and what you plug in for what you plug in for your x value. I would say that x equals 3 is obvious, but this other one, if you can't figure out what you plug in there, just do a little bit of scratch work. 2x minus 1 equals 0 means 2x equals 1 means x equals 1/2. So one of our situations we're going to use is x equals 1/2. When we plug in x equals 1/2, that allows me to cover this up. You can't see it, but I'm putting my hand right over top of it. I have b times 1/2 minus 3 is equal to 1/2 minus 13. 1/2 minus 3/2 would be 1/2 minus 6/2 is negative 5/2. B equals 1/2 minus 26/2 is negative 25/2. It looks like multiplying by 2 divided by 5. I've got my b is equal to 5. Again, other choice here, what makes this equal to 0? That's just 3. You can't see it, but I'm covering up the b times the x minus 3. This becomes a times the quantity of 2 times 3 minus 1 equals 3 minus 13. 6 minus 1, so 5. A equals negative 10 A is equal to -2. So I've got my A and my B. From here, it is extremely formulaic, although there is a mistake that I know is going to nab some of you. So here we would have A -2 over x minus 3 plus B 5 over 2x minus 1 dx. First one is not that hard. That's just going to be -2 ln of the absolute value of x minus 3. The second one is where you guys are going to get got. Technically, it would be u substitution because we have a chain of 2 here. But really, you could have it as just 5 ln of the absolute value of 2x minus 1 and divide off your chain here. So again, like one of those unofficial u substitution problems. And because we like doing it, we would have, the positive stays up top, so ln of, that will have to have a magnitude of 2x minus 1 to the 5/2 power over, that one doesn't need it, x minus 3 squared plus c. The other way that I can mess with you on this is if, oh wait, I didn't want to go away. There we go. When the degree of the numerator is bigger than the degree of the denominator, actually any time you see a rational function with the degree of the numerator is bigger than the degree of the denominator, you want to use long division to do that. I know synthetic division is also a thing that you guys know of. If you want to use the synthetic division, that's perfectly fine. But looking at this, we've got, let's see, 3x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1 divided by x squared plus 0x minus 1. I don't want to get too in-depth with reminding you guys how to do long division, but suffice to say, I use this shortcut, daddy, mommy, sister, brother. That's the acronym that I use for the order for long division. Daddy means divide. Divide your first term, 3x to the 4th divided by x squared gives me 3x squared. Mommy means multiply. 3x squared times x squared gives me 3x to the 4th. 3x squared times 0x gives me plus 0x cubed. 3x squared times minus 1 gives me minus 3x squared. Sister stands for subtract, so we change all the signs and add down the columns, so gonzo, gonzo, 3x squared. Brother stands for bring down. Let me start the party all over again. This is a recursive algorithm. 3x squared divided by x squared gives me plus 3. Multiply 3 times x squared gives me 3x squared. 3 times 0x gives me plus 0x. 3 times negative 1 gives me minus 3. I'm left with gonzo, gonzo. Oh, wait, change the signs. Forgot about that. 4. So I have a remainder of 4. So when I'm rewriting this problem out here, I'm going to have the integral of this quantity right here. 3x squared plus 3 plus 4 over x squared minus 1 dx. I will point out that those first two terms are simply find the antiderivative. So this problem is going to end up being antiderivative of 3x squared is x cubed. Antiderivative of 3 is 3x plus the integral of 4 over x squared minus 1 dx. The only thing left here is to use my whole partial fraction decomp to figure out how that decomposes. So again, looking at that as a over x plus 1 plus b over x minus 1 writing in some scratch work where I have a times the other one plus b times the other one equals the original numerator. A equals 1 produces the result. Again, you can't see it, but I'm covering up this a times x minus 1. 1 plus 1 gives me 2b equals 4, means b equals 2. Not a equals 1. It's supposed to be x equals 1, and x equals negative 1. So here, negative 1, I would have negative 2a is equal to, you can't see it, I'm covering this up, 4 means a equals negative 2. So my ultimate, this problem right here becomes x cubed plus 3x plus the integral of a. A was negative 2, so negative 2 over x plus 1 plus b 2 over x minus 1 dx. From here it's extremely formulaic. We would have x squared plus 3x plus, now let's make that a minus. We have this negative 2, minus 2 ln absolute value of x plus 1 plus 2 ln of absolute value of x minus 1 plus c, or the condensed form, x squared plus 3x plus ln of the quantity x plus, no, positive goes up top. So x minus 1 over x plus 1 squared plus c. Either one's fine. Woohoo! And I think we are done for the day. There's suggested practice problems. Peace out, homies.